Hey, So, oh my goodness, this is going to be a combustion analysis, which is I really enjoy solving combustion analysis problems. For those of you that are like me and just love getting the right answer, and you just enjoy the process, you're going to like these, okay? So this is combustion analysis. It typically involves getting a hydrocarbon, which is a compound with carbons and hydrogens. Sometimes it might contain oxygen and or nitrogen, okay? But always carbons and hydrogens. And you combust them, which means you react them with oxygen, and you get carbon dioxide and water. And based on the amount of products that you get, you can then determine the formula of the hydrocarbon that was combusted. All right, so let's look at the steps you would take to do that. So I've got an old textbook here, which is giving me a problem. And the problem says that I have Q mean, which is a compound containing only carbon and hydrogen. So I know that my hydrocarbon will have a generic formula that will be CXHX or Y, because they're not necessarily the same values. And this is called Q-mean, and it's used in the production of acetone and phenol. Combustion of 47.6 milligrams of Q-mean, combustion of, and that's going to produce carbon dioxide and water. We cannot balance this because we do not know the formula of our Q-mean, our hydrocarbon. But we do know that the combustion of this produces some carbon dioxide and 42.8 milligrams of water, okay? And the question is, the molar mass of Q-mean is between 115 to 125 grams per mole, okay? And the question is, what is the empirical formula? Let me write that up. What is the empirical formula? And what is the molecular formula? Okay, so typical problem looks pretty much like this. Now, I don't really enjoy having these milligrams. That's a personal decision. So I'm just going to make them both grams. I don't know. It's just something that bothers me is having those milligrams there. So I'm just going to multiply them both by 1,000 and work with grams. Now, what you need to notice is that our hydrocarbon contains only hydrogens and carbon atoms. And when we combust it, the only place that the water, the only place that the hydrogen goes is into the water. Now, we have to assume complete combustion, which means all of this has combusted. And this is all carbon dioxide, and none of it is carbon monoxide. But it will always be assumed and truly assumed, correctly assumed. But we know that all of our hydrogen went here because we didn't create or destroy any hydrogen atoms. We take them from this being in this compound to putting them in a new compound. We also know that all of our carbon must have gone into our carbon dioxide, right? That's not going to help us much because we don't know the amount of oxygen that reacted, so we don't know how much carbon dioxide was produced, but we're not going to need that number. If I can figure out the grams of hydrogen in the water, right, in the water that was produced, well, I know that that is equal to the grams of hydrogen in C, what we called this. Okay, so that's easy. I'm going to use what we learned, some of those molar conversions that you had to do last week, right? Or no, you had to do them in your summer assignment and then earlier this week. So if I have 42, let me get my black marker here. If I have 42.8 grams of water, I know that there are 18.02 grams of water in every 1 mole. I know that 1 mole of water, bring my labels back, has 2 moles of hydrogen. And I know that 1 mole of hydrogen is equal to 1.01 grams of hydrogen. And if I bust out my calculator and say 42.8 times 2 times 1.01 equals, divided by 18.02 equals, it looks like I have 4. Now I'm not going to round this point until I get to here, grams of hydrogen, right? That was how much is in here. It's almost also how much was in here. Now, I need to know how much carbon was in there. Well, I know that, right, question mark, grams carbon in C, right? That's what I'm going to find out. Well, I know that I have 47.6 grams, right, of that compound. My problem told me that, right? What do we call this? Y. I know that 4.79 grams of that is the hydrogen. Therefore, the remaining mass must be the carbon. Oops, make sure you get it into your calculator correctly. So that means that I had 42.81. I'm not worried about sig figs, grams of carbon. This is not an answer. This is me getting an answer. Okay. Now, what I know is that my compound CXHY apparently contains 4.798 grams of hydrogen for every 42.81 grams of carbon. Okay. Well, let's see what that ratio is in moles. So let's turn our grams to moles. Right? And let's turn our grams of carbon into moles. Right? Okay. Well, 4.798. Some of you might be thinking, why doesn't she just write down 4.798 instead of divided 1.01, which is 4.75? And that's because, I don't know, you know, there's mistakes can be made all over. I try to minimize mine and not get too impatient and to not skip corners, because I've learned that when I do that, that's when I make silly mistakes, because I make silly mistakes anyway. So I shouldn't try to skip corners, because then I'm really going to make lots of silly mistakes. Okay, I try to make grams to moles, right? This is your empirical formula, grams to moles. We didn't have the percent. Now we divide by the small, so we're obviously going to divide both by 3.565. 3.565 equals 1 mole carbon, 4.75, 0 divided by 3.565 equals, that is a 1.33 moles of hydrogen. Okay, I'm not allowed to round that number. That's looking good. A 0.33 is a good sign. So if we multiply this by 3, we get 4 moles of hydrogen. And we must also multiply this by 3, and we get 3 moles of carbon. Beautiful, we've got our whole numbers. So this must be C3H4. Okay, that is the empirical formula. And then we also need the molecular formula. So it means we need our molar mass, which was given to us way up here at 115 to 125. Okay, that's an answer. Let's circle it. So our molecular formula is going to be equal to the 115 to the 125. It was probably going to become obvious. We need to get the mass of our empirical formula, right? That's 12.01 times 3, because there's 3 carbons, plus 1.01 times 4, 12.01 times 3 equals, plus parentheses, it's just 4.04, guys. I don't need to multiply that. That's going to be 40.07. Okay, so if I divide the molecular mass that is around 120 by 40, that sounds like a 5, doesn't it? No, a 3, yeah. I get about a 3, okay? So my molecular formula must be C12, nope, times 3, times 3, times 3. So that's C9H12. All right. So I told you, if you like the problem solving, you know, a lot of chemistry is conceptual and there's no math, and students usually do not prefer that part of chemistry. This is the fun math solving. It's just kind of a logic game and understanding how to use what you have to get what you need, all right? It's not always so straightforward in this course. Sometimes you have to think outside of the box. Not too much once you learn your tricks, okay? I was gonna do 2 problems, but I think that that's probably pretty good. So sometimes, guys, no, what I was going to say is sometimes they'll also give you the mass of carbon dioxide. And that's particularly when there's nitrogen or oxygen in here, so that you have to get how much hydrogen is in here and how much carbon is in here. And then you would subtract to get the remaining oxygen or nitrogen. Or nitrogen. Sometimes if there's nitrogen in here, then there's going to be another nitrogen compound over here. But recall or notice that oxygen goes in 2 different places. So just by knowing how much oxygen is here does not mean you know how much is here, right? Because he splits up. So it would require more work, okay? You got to be careful. Those don't usually have problems like that, though. It's usually pretty simple like this in my experience. I prefer the ones that have a few more twists to them, but it's the same process, okay? Combustion analysis. Write down any questions you have. Solve this problem over on your own if you need to. I don't know. Hopefully you'll understand. See ya.